Okay, so this video will have two sample problems here dealing with fluid kinematics, the idea of acceleration, Lagrangian versus Eulerian ideas, material derivatives. So the two problems will address all of those things. So first one, this one is pretty much just related to what acceleration is and how we can have local effects on a fluid property and convective effects. So we'll see that here. So we have local acceleration and convective acceleration. But before I get too far ahead of myself, let's look at the problem statement. And this one's tough because it spans the top and the bottom of a page. But here's the system. The bottom down here, the beginning of the problem statement just says, as indicated in this diagram, we get the speed of the exhaust in a car's exhaust pipe. So the system is a car's exhaust pipe, and it varies in both time and distance, the speed of the exhaust. So the speed of the fluid in the pipe, essentially, varies in both time and space down the pipe, and that's because the engine itself is periodic, right? And so, and then there's a damping effect on the flow as you get further down the exhaust pipe. And we'll see that in the results here, this damping effect. But so let's say and you can see it in the velocity profile as well. So this is this is the functional relationship, I guess, modeled here for what the speed could be. So it has some v naught, so some typical velocity value, and then we just take that velocity value and add on a small amount, so a is 0.05, and we add on something that's decaying in x, so decaying along the exhaust pipe, and then is periodic with time. And it has a frequency here of 50 radians per second. That's what that omega means. Let's see, and our goal here is to calculate and plot the acceleration at places along the pipe for the whole time span. So you can imagine our end result is going to be a plot of acceleration versus time with 6 different lines associated with different locations in space. So let's, we should, when you read the problem statement, have an idea what you're looking for. So here's my rewording and redrawing of the system. The speed in the exhaust pipe is given by this form with some known quantities. Let's express the fluid acceleration as a function of both space and time and plot it for the appropriate values here. Well, this is 1D flow, meaning that our velocity is given in terms of just one spatial direction and then time. So I don't know how you feel about this, but maybe you could say this 2D, but it's really 1D in space, and then it's also variable in time or unsteady. But v and w are both 0, so we just have our horizontal, our x component of the velocity, whereas the y and z components of velocity are both 0. Our acceleration vector field, in general, is then given not only just by the local change in velocity with time, but also has a convective part, we call it. And this is because fluid itself can move into faster locations. So this represents a local change in velocity that just happens locally with time, or we can have a particle can experience a change in velocity just by moving into a faster or slower moving region of the flow. So then we call this convective, or the non-local part of the acceleration. So really, if you're a particle, you would just experience an acceleration as you went along, and that's a Lagrangian idea. You can think about just flowing along, and if you move into a faster moving flow, even though the flow may be steady, let's say, you'll experience an acceleration. Now, from an Eulerian approach, you can break that down into 2 parts. One, just changes in time, or just changes in space to a velocity field. And that's the idea, is that this is the transition from a Lagrangian approach to writing it in an Eulerian approach. All right, so if we write this all out, this is a vector equation. Therefore, it has 3 spatial dimensions, and it has 1 time derivative, and then this term has 3 terms itself. So we're going to see 12 total terms here. our total acceleration vector, the I component, we just write everything out. I wrote everything out to be complete. We know that V and W are 0, so that V's drop out, all the W's go to 0, and nothing changes in Y or Z. So du dy, du dz drops out to 0. All we're left with is that du dt is non-zero, and u times u dx is non-zero. This is just our total acceleration vector field, but we'll just represent this as a sub x, meaning the x component of acceleration. So our x component of acceleration is just, now we just have to run through the calculus here, du dt plus u du dx. Our time derivative, that sine will just go to cosine, and all these stay out front. This part here from v naught to the end of this bracket is just u. We're just rewriting what u is. And then du dx is just going to be this part over here, where the e to the minus bx just has a minus b out front, from the chain rule, and that's it. Going through this and simplifying things, or pulling, we notice that both of these terms have v naught, a, and an e to the minus bx in them, so we pull that out, and then pretty much everything else is just as it pulled down, right? So we can't really simplify it much more than this. But then the goal was to then plot our acceleration versus time for particular values along the exhaust pipe, so 6 lines total. And I'm going to show you that here using Matlab. You can do so using Excel or something similar as well. But as I mentioned in talking about the velocity field, so both the velocity field and we also see it again in the acceleration field, they're both periodic in time. So every single term in here has a time, a cosine or a sine with for the time part. And it decays in the x direction. So the x dependence is always this e to the minus something times x, e to the minus bx, where this b is a decay parameter. And the decay parameter being 0.2 feet over the 5 feet, right? So we have 5 feet, and the decaying parameter is 0.2, 1 over feet there, inverse feet. The decay will be appreciable then. And then we'll see periodic in time. So that's what we should expect. Okay, so here's my code. So here in Matlab, so if you're interested in looking at that, our v naught is just 8, our a is 0.05. So all of this is just plugging in the appropriate given values. We then set up an array of time, or I guess just a 1D array, so a vector of time here. And I've just done this so that we could have break down our time span. We want to go from 0 to pi over 25, and I've done this so that we break it down into 1,000 units. So we'll have 1,001 data points here to break down this going from 0 to pi over 25. And then I open up a figure, and this now represents for each one of our lines, so where x is 0, and then 1, and then 2, and then 3, and then 4, and then 5. Let's do the following. Here is just, I'm putting in that the formula that we derived for acceleration, plotting it, and then holding the figure so that we don't overwrite it. And the rest of this is all plotting. Right, so just different things to put on the labels and the titles, and you can look at this if you want, and the legend, and to put the legend in the right place. And then I do the same thing for velocity to get an idea of what that is. So let's run this once. Oops. Okay, and what just comes up is, well, first the fluid velocity in the exhaust pipe, and then over here the fluid acceleration. And you could save these as whatever you like. I like EPSs, put them into a Word document, and I generated this. This might be a nice thing to present here, that our code, the code that is important here, is shown here, just to plot what the acceleration field is. The fluid velocity was a little bit of bonus, and then I have the plots down here. Now to just quickly discuss this, again, we see that periodic in time. Remember, these are plots of velocity and acceleration per time, and no matter what line you choose, this is periodic. We see it coming back to the starting point as we get to the end of this period, whether it's velocity or acceleration. The spatial dependence now is shown by the different lines, and you can see here at the beginning of the pipe, so early on, closer to the engine where the exhaust is being generated and the flow is being forced. from that engine, we see a much stronger effect, right? So we reach higher amplitudes for velocity and accelerations. And as we go further down the pipe, so from 0 feet to 1 foot, 2 feet, 3 foot, 4 foot, 5 feet, these effects are less and less and less, and that's showing the exponential decay nature of the the kinematics within the pipe system here. There is an interesting point here where in time here everything kind of comes down to the same, no matter where you're in the pipe, you have the same velocity. And also at that two other instances in time, we get no acceleration anywhere in the pipe. But in general, I think the most useful thing from this is just representing this periodic nature in time and exponential decay nature in space. Okay, so that'll be the end of that problem. Let's go to another problem here that 4.54, which will then we'll be able to talk about the difference between Eulerian and Lagrangian approaches, as we mentioned in the first problem here, but then also introduce this material derivative, which is what we did with the acceleration. It's the material derivative of velocity to get to acceleration. But here, let's pull up the problem statement in the book. It's just a paragraph. A gas flows along the x-axis with a speed given, but the speed depends on along the x location, and the pressure also depends on the x location. So the velocity goes as x, and pressure goes as x squared. X is, we're in SI units here. So let's determine the rate of change of pressure at a fixed location. So let's be clear on this wording. We're determining the time rate of change of pressure at a location in space. And then the second part, let's determine the time rate of change of pressure for a fluid particle that goes past this location in space. So in 1, we want to know if you put a pressure measuring device there at 1, what is the time rate of change of pressure? This one is saying that if you follow a particle and it passes through 1, x equals 1, what does that particle pressure change with time? So they're two different things, right? Okay, so my restatement is just gas flows with this and this, and then we need to determine this, and then we need to determine this. All right, well, what do these mean? This is saying that what is the time rate of change of pressure at a fixed location at x equals 1 meter, right? Well, if we look at pressure, it doesn't change with time. So if you stick a pressure measuring device in there, and that's an Eulerian approach to a fluid system, thinking about everything as depending on both space and time, and you can put sensors at many, many locations to get an idea of how the fluid, properties or the fluid variables change with space, and then as you measure things with time, you can get them as time, right? So, but by putting fixed things, by putting a fixed grid on your system, that's an Eulerian approach. However, and then nothing here depends on time. So each of those pressure measuring devices won't change in time. They'll just have a different pressure, at the different locations in space. But since we're at a particular one at 1 meter, it's not going to. The pressure it's measuring won't change in time. However, if instead you followed particles around, and now this is important because particles, or a lot of the fundamental laws that will then apply to fluid systems are written for, a Lagrangian approach, for as they move, as a particle moves, does its mass change, does its momentum, how does its momentum change, how does the energy of a particle change, right? So we want to analyze things in an Eulerian setting where we can basically think about keeping a fixed grid and measuring fluid properties at fixed locations in space and time. But really, the nature of fluids and the fundamental laws that govern fluids are following particles. As particles move around, does their mass, momentum, and energy change? So we need to have a way to talk between the two, and that'll be later on in this chapter, in chapter 4. But for now, we're just showing that there will be a difference when you think about things in two different ways. And so this is now a Lagrangian approach. What is the total rate of change if I'm a particle flowing through x equals at 1 meter. So this is now the material derivative of pressure. It has a local part and a convective part. It's the time rate of change of pressure at that location in space, which we found from up here is just 0, right? And that's just because pressure doesn't change with time. But that particle will also be moving with the flow, and the pressure can then change in space as it flows, then relating to that particle then experience a pressure change with time. All right, so if we plug everything in here, u is just 5x, dp dx, we just take our p and take dp dx is just going to be 2x times this 10 quantity. I've rewritten my units here a little bit differently than they do in the book, but I think this is more consistent the way I've done it here. But in the end, if you put all this through, you get that the change of pressure, the time rate of change of pressure for a particle that is now passing through this point, even though the system is steady, is 100 Newton per second meter squared. All right, so written out here, the fluid particle experiences a pressure increase as it flows through this location in space, not because the pressure at that location in space is changing, but because it's just flowing into a higher pressure region. As it goes further along x, pressure is going to get higher and higher and higher and higher, and it's flowing in the positive x direction because the velocity is taking it there. So that particle is just flowing into a higher pressure region, and therefore that particle's pressure will increase. And this is a Lagrangian approach, as I said. All right, so in general, even though the system is steady, the general statement we can make out of this is even though a system is steady, meaning that local time derivatives are 0, particles themselves can have property and kinematic variable changes as they flow through the system. So particles experience time changes even though the system itself is steady.